All right, so 7.3 guided notes is all about radicals. Radicals are just roots, and I know you've all heard of roots. So let's talk about what the pieces of a radical expression or a root expression are. So down here toward the bottom of the screen, I've written out a radical or a root of B. Now, notice there's also this little letter N here. That's important. So I've used color to kind of code three pieces of this expression. The red part is actually the radical or the root symbol. No radical is complete without the other two pieces, though. The green part, the B, is called the radicand. Now, one thing we're going to talk about today is how similar radicals and exponents are. So, another way to think of a radical or of a radicand is as a base. That's why we use the letter B here. So, you remember what a base is? A base is what's being affected by an exponent. A radicand is what's being affected by a root. Now, roots and radicals are very, very similar to exponents, and we'll talk about that here in a few minutes. So when you think of what's inside the radical, try to draw a connection between a radicand and a base. Finally, we've got this little number on the outside of our radical is called the index. It's a number that's outside of the radical, and it tells us what type of root we're taking. So you've heard me use phrases like square root, cube root, fourth root, fifth root. That all depends on the index. So down here, if we want to label the parts of this expression, this blue N is called our index, and that will always be a number. Okay, it won't be a letter like N, it will be a number. So there will be a 3 or a 4 or a 5 there. The red part is our radical, and every single root has this part in it. And then finally, the B, we call that our radicand. It would not be wrong to call that a base, aka base. So if you call it a base or a radicand, you are correct. So roots and exponents are opposites of each other. Think about adding and subtracting. Those are opposites. They undo each other. Multiplication and division. Those are opposites. They undo each other. Roots and radicals are opposites, or I'm sorry, roots and radicals, radicals and exponents are opposites. They undo each other. So roots and exponents are opposites. Let's talk about how to evaluate a root. And this will seem kind of similar to what we talk about with exponents. I'm going to scroll out a little bit, so it might be kind of hard to read on the screen, but you can look at your paper. Evaluating roots requires us to ask, what can I multiply to itself n times to equal the radicand? So this is a long question, but let's break it down. N is our index. So the first thing we need to do is figure out what our index is for each particular problem. Sometimes there will be no index written. You'll just see a symbol like this, and there's no number written inside of it. That just means square root. Okay? The most common root you will see is a square root. We don't usually write the number 2 in here when it's a square root. Kind of like if you have an exponent of 1, you don't write the 1. It's our most basic root. You don't have to write the 2. So if there's no index written in your root, assume that it's a square root. Then we ask, what do I multiply to itself that many times to equal the radicand? So let's start with example 1. Example 1 doesn't have an index. So we assume this is a square root. So the question we ask ourselves is, what can I multiply to itself 2 times to equal 25? Any thoughts? Somebody want to yell it out? 5. I can multiply 5 times itself twice, 5 times 5, to give me 25. So my answer is just the square root of 25 equals 5. So I'm going to take a different colored pencil real quick, and I'm just going to write out another way to think about this. 5 times 5 is 5 squared. 5 squared equals 25. So if the square turns a 5 into a 25, then the square root turns a 25 into a 5. That's what we mean when we say that these two things are opposites of each other. Roots and exponents are opposites of each other. They undo each other. So we'll do a few more examples like this. In example 2, we have a cube root. This is a root that has an index of 3. So in this question, we're asking ourselves, what can I multiply to itself 3 times to get the number 64? And you might have to think about some of these. You could even use a calculator. So pull out a calculator and plug in 2 times 2 times 2. Pull out your calculator and plug in 3 times 3 times 3. Plug in 4 times 4 times 4. 5 times 5 times 5. See if you can get an answer. And I just got some eye contact. Does anybody ever here know what the answer is? Do you know it? Did you just? Yeah, 4. When you plug in 4 times 4 times 4, it's 64. So a lot of these problems, heads up, you will be using a calculator to simplify these, okay? Most people can't do this sort of thing in their head. So be prepared to have a calculator handy when you're working on this type of problem. So yes, 4 times 4 times 4 is 64. So the cube root of 64 is 4. Another way to think about this, 4 cubed is 64. So the cubed root of 64 is 4. They are opposites. They undo each other. One more problem like this. Nope, 2. I was wrong. So for the next example, example 3, we want to find a 4th root. Our index is 4. So we need something that multiplies to itself 4 times to equal 81. This again might be a calculator type of problem. Grace, do you know what the answer is? It is. So 3 times 3 times 3 times 3 gives us 81. And you can always verify these by checking on a calculator. So that means the 4th root of 81 is 3. 3 is the number you have to multiply to itself 4 times to get 81. And that makes sense because these multiply together to give you 9, and these multiply together to give you 9. 9 times 9 is 81. That all fits. All right, last one of this type. Now we're looking for a 5th root. So we ask, what number do I multiply to itself 5 times to equal 32? Hopefully this one won't be too bad. Can anybody else tell me? Yeah, what is it? It is 2. So 2 times 2 times 2 times 2 times 2. That's a lot of them. But yeah, the 5th root of 32 is 2. Fantastic. Now, although some of these got a little hairy, in general, these are the easy problems. These are the problems that we can evaluate. We can get a number as our answer, all the roots disappear. The problem is not all radicals can be evaluated. Instead, we simplify those. So you can't always get a nice, neat, round answer for every single root that you come across. But you still have to make sure that your answers are always simplified. Think about it this way. If you're ever dealing with fractions and you end up with, say, I'm going to erase this, but let's say you end up with 5 over 10. You wouldn't write your answer like that. You'd always simplify it. You'd divide the top by 5 and the bottom by 5, and you'd write your answer as 1/2. Radicals are very much like fractions in that you always simplify them before you present your answer. So now we're going to talk about how to do that. We've got 3 steps we're going to learn. And as we're talking about each step, we're going to work with the example on the right. So we're going to simplify the square root of 24. The first thing we want to do is just figure out if it's a perfect square. So like, does this have a nice, neat, round answer? Well, think about it. 4 times 4 is 16. So that doesn't work. 4 is too small. 5 times 5 is 25. That doesn't work. That's too big. 24 is kind of in between. So we can estimate that it might be around 4.9 because 24 is really close to 25. But it's going to be a decimal number, and it's not going to be nice and neat and round and pretty. So this one cannot be evaluated. We don't get a nice numerical answer. So we're going to have to simplify it instead. Here are the steps to simplifying a radical. First, you factor the radicand. In this case, our radicand is just 24. So we're going to take the number 24 and we're going to factor it using a factor tree. Now, I'm sure you guys have all seen things like this. We use red. You take 24 and you split it up into two things that multiply together to give us 24. So just yell something out, anybody. 6 times 4. I love it. Okay, 6 times 4. There were other choices. We could do 8 times 3. We could do 2 times 12. But 6 times 4 works really well. Can 6 be split up again? Yeah, sure. 2 times 3. So 4 can be split up again. So this 4 over here can split, it can split into 2 times 2. 2 cannot be split up again because the only thing you could split 2 into would be 2 times 1. But then you could do it again and split the 2 up into 2 times 1. And then you could do it again and split it up into 2 times 1. And you would just go forever. So if you get to the point where you can only split it into something times 1, then you can stop. It's called a prime number. 2 is only made up of itself times 1. 3 is in the same situation. You can't split that 3 up anymore except into 3 times 1, which is pointless. So all of our branches have now ended at a prime number. So what we're going to do now is we're going to rewrite our radical, but instead of 24, we're going to rewrite 24 as 2 times 2 times 2 times 3. It's just factored. And it's still 24. If you multiply those together, 2 times 2 times 2 times 3, it's still 24, okay? We haven't changed it. So now we're on to step 2. This is a kind of weird rule, but we'll explain it here in a minute. Pairs of factors can be pulled out of the radical. So what you're going to do now is you're going to go through and circle any pairs that you see. I see a pair of 2's, and that's it. Then you're going to pull that pair out in front of the radical. When that happens, you only bring a single item from the pair. So you've got a pair on the inside, which has 2 factors in it. But when you pull it out, you're bringing the pair as a single unit. So out in front of the radical, we're going to write just a single 2. And then inside the radical, left over, we still have a 2 times 3 that's still inside. So those didn't come out. So we can simplify this down one more time. The 2 times 3 can combine. Oh, you can't see that behind my picture, can you? The 2 times 3 can combine inside that radical and just give us 2 times radical 6. So that was step 3. So our answer is right here, this 2 radical 6. And what in the world just happened? How does the square root of 24 equal 2 times the square root of 6? What does that mean? Well, let's think about this a slightly different way. 24 is the same thing as 6 times 4. Kendall helped us see that earlier. So we can rewrite this as 4 times 6. 6 is not a perfect square, but 4 is a perfect square, right? If we rewrote this as the square root of 4 times the square root of 6, which we're allowed to do, this one actually simplifies. The square root of 4 is just 2. We can calculate that. We can evaluate it. So the square root of 4 becomes a 2, but then we still have this square root of 6 that we can't do anything with because that one's not a perfect square. 2 different processes to get you the same answer. And you might be looking at this right now thinking, well, wow, the second one was way easier. Why did we do it the first way with the factor tree and all of that? Well, the second way is a lot easier when your number is small, like 24. But when your number is big, like 3,600, the first way is easier. And we're going to do some examples to show you how this works. Also, some of our examples will have X's and Y's in them. And so it's easier to use the factor tree method on those types of examples as well. So let's just dive into these examples. We'll start off with an easy one. Let's simplify the square root of 18. First, make a factor tree. So let's see, two things that multiply together to give me 18. How about 2 times 9? Now 2 is done. We can't factor 2 down anymore because it only factors down into 1 times 2. We don't care about 1. Then 9 can factor down into 3 times 3. And both of these 3's are now done. I like to circle them when they're done. That helps me. So we rewrite the square root of 18 as the square root of 2 times 3 times 3. If we have any pairs, you can circle that pair and then pull the pair out front. And think about why we're doing this. We circled a pair of 3's, right? 3 times 3. Well, what's 3 times 3? 9. 9 is a perfect square because it's made up of 3 times 3, right? It almost feels a little circular. Anything that's made up of something multiplied to itself will be a perfect square. That's why we're circling pairs, because these pairs make up perfect squares. So when we pull it out front, we'll have a 3 out there, then our square root symbol, and inside our square root, we still have this number 2. But there's nothing else in there with the 2. So our answer is 3 radical 2. That's it. For number 2, our radicand is getting a little bit more complicated. We're looking at a 75x squared. So we haven't done one like this before with variables inside. Let's start this problem off the same way we would start off any problem, by factoring 75. So once your numbers start to get a little bigger like this, it can be helpful to use a calculator to do your factoring. Can anybody either think of something or use a calculator to find two numbers that multiply together to give us 75? 25 times 3. Yeah, because if you had 3 quarters, you'd have 75 cents. So 3 is done, but what about 25? Let's split that up again. Somebody want to yell it out for me? 5 times 5. 5. Whoops, that circle got a little weird. So the 5's are done now too, because 5 can only be split up into 1 times 5, which is pointless. So we're going to stop here. We will rewrite our radicand, which started out as 75x squared. This 75 splits up into 3 times 5 times 5. The x squared also splits up. X squared is x times x. That's what an exponent tells us to do, is to multiply that thing to itself, right? So x squared gets split up into x times x. Whatever the exponent is tells us how many x's to put down, right? So these can be split up too. Step 2 remains the same. Circle any pairs and pull the pairs out front. So I see a pair of 5's and I see a pair of x's. What that means is we're going to pull a pair of 5's out front and we're going to pull a pair of x's out front. You can pull out multiple things. So in front of our radicand, in front of our radical, we're going to have a 5 times x, and inside the radical, we're left over with just a 3. So our answer looks like 5x times the square root of 3. The next problem is even more complicated, but I'm going to go through this one a little bit more quickly since we just saw a similar example. First, we're going to take 20 and split it up using a factor tree. I'll start with, how about 4 times 5? The 5 is done, but the 4 can split up one more time into 2 times 2. So if I rewrite this radical expression, the 20 gets split up into 2 times 2 times 5. The x cubed gets split up into x times x times x. And the y to the 4th gets split up into y times y times y times y. You have to split up every single part. And now we circle pairs. So I see a pair of 2's, a pair of x's. Careful, you only circle 2 of those x's. I see a pair of y's and another pair of y's. Okay, we got a lot of pairs in this one. So I'm going to be pulling out a 2, an x, a y, and a y, all go out front. 2x, y, y, all out front. But then inside of the radical still, I've got some stuff left over, some stuff that didn't get pulled out front. A 5 and an x, 5x. One more thing we need to do here. This is step 3. If you can ever simplify anything, you always need to. So looking out front right now, see these y's, y times y? We wouldn't leave our answer like this. We would actually combine those. And we learned how to do that last week. Y times y gives us y squared, right? Because you add your exponents. So this becomes 2xy squared times the square root of 5x. Big, complicated answer. Okay, we have one more example to do on this page. We'll have a backside too, but that backside won't take us very long at all. For example number 4, we're dealing with the square root of 3,600. So for a problem this big, we definitely need to use a factor tree to figure out what's going on inside of it. Now, a trick I like to use when I'm factoring really big numbers, if your number ends in a 0, you can always achieve your number by multiplying 10 to something to get your number. So since this ends in a 0, I know that 10 times something equals 3,600. And all you have to do is kind of take a 0 off to figure out what that is. I'm sure you guys have learned this trick where if you multiply 10 times something, it just adds a 0 at the end. That's basically what this is, but in reverse. All right, let's keep going. This 10 splits up into 2 times 5, which are both done. The 360 can split up using the same rule because it ends in a 0. So that can be split up into 10 times 36. The 10 splits up 2 times 5, déjà vu. The 36 can split up. We have options, but I'm going to go with 6 times 6. And the 6's can now both split up into 2 times 3. So I know that was a lot of work really fast. I'll give you guys a second to catch up. Okay, so now we rewrite our radical expression in factored form. And I've got so many factors here, I'm going to cross them off as I write them down. Otherwise, I'm afraid I'm going to forget something. So we're going to start with our smallest numbers. So I'm going to write in 2 times 2 times 2 times 2. That was 4 2's. Then I've got a couple of 3's. So we'll do 3 times 3. Cross those off as I use them. And then we've got a couple of 5's. Times 5 times 5. Okay. Any pairs can be circled. So I see a pair of 2's, another pair of 2's, a pair of 3's, and a pair of 5's. Everything paired up. So what happens here is we're going to move a 2, a 3 and a 5 out front. 2 times 2 times 3 times 5. And then what's left over in the radical? Absolutely nothing. I mean, technically, it would be like there's a 1 in here. You know, we could pretend that you had like a times 1. So there'd be a 1 left over, but the square root of 1 is just 1. So that goes away. So we don't think about this or this. If everything in your radical simplifies out, if it all pops out, if it all pairs off and pulls out of the radical, then that means that this was a perfect square root. We could have evaluated this. You could type the square root of 3600 into your calculator and gotten an answer. And that answer will be 2 times 2 times 3 times 5, which is 60. I'd like you to flip your packets over, or not flip them over, but flip to the next page. We've got about a half a page left to do, but this part is pretty darn easy, I assure you. So I mentioned at the start of class that radicals and exponents are opposites of each other. They're flip sides of the same coin, so to speak. You can actually write radicals as exponents, and you can write exponents as radicals. So there's a phrase here that you're going to want to know. It's rational exponent. All that means is an exponent that is a fraction. So if you hear us talking about rational exponents, we're talking about exponents that are fractions. Exponents that are fractions and roots are the same thing. And we're going to talk about why that is and how that works here in just a moment. First, we're just going to talk about how to convert back and forth between the radical expression and the exponent expression. So let me zoom in here as much as I can. On the top left, we have a radical with a base that has an exponent and an index. Actually, I'm not going to do that in red. I'm going to do the index in red and an index. If we wanted to convert this radical into an exponent, we would start by rewriting our base with its exponent over index. Basically, you take whatever is inside the root and you just make an exponent expression out of it, but the index, the little red n, has to form the bottom of a fraction in your exponent. So it works in the other direction as well. So now looking on the top right, if you start with an exponent, if you start with a base to an m over n, you can take this and you can write it as a radical. So what we do there is we start by drawing our radical symbol. We put our base, b, and its exponent, m, inside the radical. That is our radicand. And we put n, the index, on the outside. So these things mean the exact same thing. You can go back and forth between the different forms. There are two more examples here I wanted to show you, and that is, what do you do when you have this extra a out front? So this wouldn't necessarily be a. This might be a number. It might be a 2 or a 5. It could be an x. It could be a y. A is not part of the radical. It's not part of the radicand. So when you're converting the radicand into an exponent, the a is not part of that. It's not part of it at all. So all we would do is rewrite the a in the front. But then the base to the m over n would be separate. They would just be multiplied. A is not part of the base. So when you're going in the other direction in particular, you have to be very careful. So where we have m over n here on the bottom right, This m over n is an exponent. What is the base of that exponent? Anybody? What's the base of the exponent in this example? N is the index. What's the base of the exponent? The base is the thing that the exponent is directly touching. Yeah, I think you just said it. B. It's just the B. B here is the base. A is not part of the base. A is separate, A is in front. Remember, the base is only what the exponent is directly touching. So when we go to convert this into a radical expression, the only thing that goes inside the radical is the base and its exponent. The n is here. So that A basically just belongs out front. We just throw it there out front. That's not part of the radical expression. It's just being multiplied to the radical expression. So we will do some examples like this. We're going to rewrite each of these four radicals in exponent form. So for example 1, we start out with a radical and we want to write this as an exponent. So we start with our base and its exponent, and we put that over our index. So this should be x to the 3 over 4. It's as easy as that. That's all you have to do in this problem. We rewrote it, we are done. For problem 2, we write our base and its exponent. What is its exponent? What is the exponent of A? 1, very good. It's not written here, but there's a 1. Wherever you don't have an exponent, you can just put a 1 there. So this is A to the 1 over 3. Now for example 3, we have a cubed root of 14 squared. So we start with our base, 14, and its exponent, 2. And then we put the 2 over the index, which is 3. 14 to the 2/3. These aren't super bad. Now number 4, this one's a little tricky. We start with our base, x, and its exponent, 5, and we put that over our index. Well, what's our index here? With square roots, if our index is missing, we assume that our index is 2. That will take some getting used to. So our index here that goes at the bottom of the fraction is a 2. Okay, we have 5 more examples. These won't be that bad. For example 1, we're going to go in the opposite direction. So here we have an exponent, and we want to write it as a radical. So it's going to be hard to see it on the screen because these numbers are really small, but look at your packet. You can see it better on there. This is b to the 3 over 8. So our base is b, our exponent is 3, and our index is 8. So this is where all of those various pieces go. The 8th root of b cubed. We could do the same thing for number 2. A to the 1/3 power. I'm going to start by drawing my radical symbol. My base, a, goes inside. Its exponent, 1, goes along with it. And the index, 3, goes on the outside. So a to the 1/3 is the cubed root of a to the 1. Now, we don't have to write the 1. You all know this. We can just write this as the cubed root of a. And that's fine. Either way is fine. Number 3 is trying to trick you. In number 3, we have to pay very close attention to what the base is. So we do have a fraction exponent, x to the 1/2. The base of the 1/2 is just x. The 6 is not part of the base. So when we go to rewrite this, we're just going to write the 6 down. Like that doesn't come along with us into the radical. The radical expression is just going to have our base x, its exponent 1, and the index 2. There are a few things here we don't have to write. When you have a square root, you don't need to write the index of 2, right? Because that's our basic standard root is the square root. So you don't need to write that 2 in there for your answer. And you don't have to write the exponent of 1 because that's our basic standard exponent. So our answer can just be 6 square root of x. 2 more problems. We're almost there. For number 4, we have a very similar problem, very similar to number 3. First, you need to make sure you know exactly what your base is. And in this case, it's just the y. The exponent is just touching the y. So we'll rewrite the 3 out front, sure. But inside the radical, we're only going to have our base y, its exponent 4, and then on the outside, our index of 5. One more example. Number 5 and number 4 are almost identical. Almost. 3y to the 4/5. The difference is that set of parentheses. So some of you might be able to see where this is going. When we are examining a rational exponent, you have to identify its base. Well, this exponent is touching a set of parentheses, which includes all of this whole expression, parentheses, 3y, parentheses. So when we go to convert this into a radical, the base is all of this, parentheses, 3y, parentheses. Do not forget those parentheses. You need them inside of your radical. They have to be there. If you don't have these there, you will be wrong. Its exponent, which is 4, and then your index, your index, which is 5. We might have an additional step to complete, though. I see some people putting their packets away. We're not done with this problem. The reason why those parentheses were so important is because, look at this. We now have an expression to an exponent, and we talked last week about how this is not considered simplified. We have to actually distribute. So this becomes 3 to the 4th, y to the 4th. And if you plug into your calculator, 3 times 3 times 3 times 3, you get 81. Come on, you guys know I'm always going to throw a curveball at you at the very last problem. So sometimes on these types of problems, you have to do a little bit more simplifying, a little bit of additional manipulation to get your answer into the right form.